So chapter 16, we're almost done. It'll be okay. Let's summarize the things we've done so far. Some of the things that we've done so far. So we started out the chapter with some equations. So 1.00 times 10 to the negative 14th is equal to H3O plus times OH minus, the equilibrium constant expression for water. We know the definition of pH when we're calculating it is the negative log of the hydronium, the H3O plus molarity, and hopefully we remember that everything that's in brackets in any of these equations has to be in molarity. Okay. And then we added POH, which is a different acid-base scale, is equal to the negative log of OH minus, and that pH plus POH is equal to 14.000, which is really just a redo of the first equation, just negative logging it. Okay, so those are equations. Then we started talking about how to calculate the pH of different types of chemicals. So we are breaking chemicals down into 4 categories: strong acids, strong bases, and weak bases. So if we look at strong acids first, we have to memorize there are 7 of them, and we have to know all 7. So not just memorize the number 7, but know all 7 of these: hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric acid, perchloric acid, nitric acid, and sulfuric acid. And we need to know those 7 and know that they're strong acids. We also need to know that being a strong acid means it dissociates 100%, which means the molarity of the strong acid is going to be equal to the molarity of the hydronium ion. This is only true for these strong acids. These are the strong acids. Okay. So if you're asked to calculate the pH of one of these acids, you'll take the molarity that you're given, substitute that in for H3O plus, and solve for pH. Okay. Next, we talked about the strong bases. There are 8 of them. Now, all of them contain hydroxide. Okay. Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. Then we have calcium hydroxide, which contains 2 hydrogens because of the charge of calcium, strontium hydroxide, and barium hydroxide. These are the 8 strong bases. When they're added to water, they dissociate 100% of the time. So, based on the molarity of a strong base, well, if we have a strong base with 1 OH minus, so that's the first row of them, right? The lithium, sodium, potassium, rubidium, cesium. The molarity of the base is equal to the molarity of hydroxide. If you have a strong base with 2 hydroxides, you take its molarity times 2, and that will give you the molarity of the hydroxide, because 1 molecule of calcium hydroxide, when it dissociates completely, breaks into 3 ions. The calcium, which we're ignoring right now, we don't care about, and then 2 hydroxides. So 1 calcium hydroxide molecule becomes 2 hydroxides. That's why we have to take its molarity times 2. Okay, strong acids, strong bases. We talked about those. What about weak acids? So weak acids, which we can identify as being an acidic compound, starts with a hydrogen or has the word acid in its name, but is not one of the 7 strong acids. That's why we have to memorize the 7 strong acids. I call all weak acids HA. There are hundreds or thousands of these weak acids. So I'm just going to say, okay, once I identify the chemical as is a weak acid, from then on, the whole problem, I'm calling you HA. So weak acids go to equilibrium. So this is the equation that weak acids follow when they go to equilibrium. The weak acid, HA, plus water, equilibrium, there we go, to make hydronium ion, and A minus, which is just the conjugate base of HA. So since it goes to equilibrium, it has an equilibrium constant. Products over reactants, so hydronium times A minus over HA. Water is being ignored because it's a pure liquid. Okay, so the last 2 videos, so 4 and 5, We spent a lot of time going over examples with these weak acids. We used all of our tricks from chapter 15, things like ice tables. We had to use the quadratic formula, although we did learn a shortcut that can sometimes be helpful. Okay, so I said we have to break every type of chemical, or every chemical when we read a question, into one of 4 categories: strong acid, weak acid, strong base, weak base. Well, one of them's obviously missing from here, right? We haven't talked about weak bases yet. So let's do that. Weak bases, there are hundreds or thousands of weak bases, which again is why you have to memorize the strong bases. I abbreviate weak bases as the capital letter B, just like I abbreviate weak acids as the HA. Okay, so weak bases, just like the weak acids, do not dissociate 100%. They do not, or they don't accept protons 100%. They don't behave as bases 100%. So they go to equilibrium. So capital letter B stands for whatever the weak base is. It starts out very similar to the acid one, right? It's the weak thing plus water. Yeah, but remember bases, they are different than acids. Bases accept protons, acids donate them. So on the other side, the B for base has gained an H+. That H+ had to have come from the water because that's the only thing at the beginning that has hydrogens. So what's left of water is OH-. So again, this goes to equilibrium. So we have an equilibrium constant. We're going to call the equilibrium constant for bases Kb, super original, right? So Ka for weak acids, Kb for weak bases. Strong acids and strong bases do not have equilibrium constants because they don't go to equilibrium because they break apart 100% of the time. Okay, so everything we did with the weak acids works the same with weak bases. We're going to do ice tables. We're going to solve for X, all that kind of stuff. But at the end of the question, or the question is going to usually ask, typically it's one of 2 things. Solve for the equilibrium constant, so it'll be solve for Kb, or what is the pH? Now, if we look at this equation, with the weak acids, we used the hydronium, the H3O plus molarity, to solve for pH. This equation doesn't have H3O plus in it. I know this is HB plus, that's not the same. Okay, the closest thing in this equation to H3O plus is hydroxide. So at the end of doing an ice table or whatever you have to do for a weak base, you're going to be interested in the hydroxide ion molarity, and then you're going to have to convert that into a pH, which can happen one of 2 ways. The POH and then the pH, or you can convert the OH to the H3O plus to the pH. So backtracking, you're either going to use this equation and this equation, or this equation and this equation to convert the OH minus. Okay, so this is just an example of what it would look like with an actual chemical there. But that's the equation. Base plus water, arrow OH minus, and HB plus. So in this case, B was NH3. So that's why it's now NH4 plus. It has an extra H plus on it. Okay, so in Appendix D, that beautiful appendix that had the list of all the acids, not all of them, but many acids, many of the weak acids, with their chemical formula, their name, and then their Ka1 or Ka2 or Ka3. On the back of that, so on the back page of Appendix D, is a Kb table. Similar table, but for weak bases. But you'll notice if you look at that, the Kb table is very small. Like the Ka table takes up the entire front page. All of it. The Kb table is not very long, and we're going to see why here pretty soon. I'll show you how we can, come up with more Kb values that we were not given. But just like with Ka, the equilibrium constants for weak bases are small, but the larger the Kb value, the stronger the base. Because it's a ratio of products over reactants, and the stronger the bases are going to make more products. Okay, so just like with Kas, you're not memorizing these. These are numbers you would look up. Just like with Kas, if the equilibrium constant is times 10 to the negative 8th or smaller, we can do our shortcut where we cut off the trailing x's. Okay, so that shortcut works for Kb's as well. So let's jump in. Okay. We'll read the question, and then I want to talk over something that I forgot to mention before. What is the pH of a 0.15 molarity solution of NH3? Well, the Kb needs to show up somewhere. I don't know where that's going to show up, maybe at the bottom. But when we read the question, the first thing we're supposed to do is identify which of the 4 types of chemicals it is, right? A strong acid or a weak acid, or a strong base or a weak base. I feel like we've talked through the first 3 pretty well. The strong acids, you memorize them, that's how you know. The strong bases, you memorize them, that's how you know. The weak acids, well, it starts with a hydrogen or has the word acid in its name, but it's not one of the 7 strong acids. So with the weak bases, you'd think like, oh, well, it has the word base in its name and starts with, or has an OH or something. Because of the Bronsted-Lowry definition, things can be bases as long as they accept a proton. They do not have to contain a hydroxide. So here's my real fancy, real scientific suggestion on how to identify a weak base. Process of elimination. You've already decided it's not a strong acid because you memorized those and it's not one of them. It's not a strong base because you memorized those and it's not one of them. It's not a weak acid because it doesn't have a hydrogen at the beginning or the word acid in its name, but it's not one of the 7 strong ones. It's other. It's not those things. That's going to make it a weak base. So looking at NH3, it's a weak base, not only because I'm telling you that, because this is an example after the weak bases, but also because it's not one of the other 3. Okay, so from here on out, NH3 to me, you're capital letter B. You're a weak base, I'm calling you B from now on. So I just copied down the equilibrium constant expression from the previous slide. We're going to use this where NH3 is now B, okay? And, oh, there we go. The equilibrium constant expression, the products over reactants, I would have told you in the question that Kb equals 1.8 times 10 to the negative 5th. Okay, so we were given that. So, looking back at the question, what is the pH of a 0.15 molarity solution of this weak base? Well, to solve for the pH, I cannot use the molarity of B to solve for that because weak bases, their molarity is not equal to the molarity of OH minus. What we do is we have to solve for the molarity of OH minus at equilibrium. That's what we need to do. So we're going to need to set up an ice table, set up our initial, our change, do all of our math with everything. Okay, so I'm going to take my equation. There it is, the same equation from before. And I set up my ice table. I ignored water, right, because it's a pure liquid. This is where the arrow would be. So for my initial values, well, the weak base, I can take the number from the question and throw it in there. It was, what, 0.15. There we go. For HB plus and OH minus, there were no initial values given, so we know that those are 0. For the change row, we know one side of the arrow is going to have a positive change and one side of the arrow is going to have a negative change. So looking at this, the products start with 0, which is how I know that the right-hand side, I know my directions, are going to have the positives and the left-hand side is going to have the negative. And there's 1B, so 1x, there's 1 HB, so 1x, and 1 OH minus, so there's 1x. Beautiful, we've got our initial and our change. Well, at equilibrium, we don't have any numbers. Okay, we were not given any equilibrium concentrations. We were not given any pHs that we could turn into equilibrium concentrations. Instead, we have no information. But we do know that the initial row plus the change row is equal to the equilibrium. So I can bring all of this down. For B, 0.15 minus x. For HB, 0 plus x, which is just x. And for OH minus, 0 plus x, which is x. So we've done my ice table, but I don't have what I need. What I need is a number for that. So this is when we know we're going to have to plug them into the Kb expression, the equilibrium constant expression, and go about doing our math. So this is when we're starting to think, oh crap, it's going to be a quadratic formula. So before we do that, we need to stop and think. Go back. I'm going to backtrack. This is going to be fun. Look at our equilibrium constant, 1.8 times 10 to the negative 5th. Can we do our shortcut? No. Our shortcut's times 10 to the negative 8 or smaller, times 10 to the negative 8, times 10 to the negative 9, times 10 to the negative 10. So we cannot call B 0.15. B has to stay 0.15 minus x. So what I'm going to do next is take my equilibrium constant expression and substitute in the equilibrium values for all 3 chemicals. And I'm going to have to cross multiply, then distribute, and then get them all on the same side, where the A value of this is 1, the B value is 1.8 times 10 to the negative 5th, and the C value is negative 2.7 times 10 to the negative 6th. And then I need to plug this into the quadratic formula. So you're just going to have to believe me that when I did that, I got 1.6 times 10 to the negative 3rd. Okay, so I got my value for x. Awesome. We needed a value for x. So going back to my ice table, what I need is the molarity of OH minus. That's what I need to solve for the pH. Well, we know that OH minus is equal to x. We now have that number. So OH minus is 1.6 times 10 to the negative third. So what I'm going to do now is use that value to solve for pH using the equations we did at the very beginning of the chapter. So either using POH and then subtracting from 14, or using OH minus to solve for hydronium ion and then taking the negative log of that. So in this example, I used the OH minus to solve for POH, which had 2 sig figs, so my value had 2 decimal places. That's not my final answer. That's the POH. The question specifically asked for pH. So I've got to subtract from 14, and I get 11.20. So at the end, this pH, is it acidic, basic, or neutral? Well, it's greater than 7, so it's basic, which makes sense for a weak base, right? What I don't want to see happen is if you get to this point and you're like, oh, I'm done, I got a number. If that was a pH, it's not, it's a POH, but if you mistakenly thought it was a pH, isn't 2.80 acidic? And if this chemical is a weak base, does it make any sense for a weak base to be acidic? No. So it's a good idea at the end of these calculations to always look at your pH and make sure it makes sense for your situation. If the chemical you're looking at is a strong acid or a weak acid, the pH should be acidic. If it's a strong base or a weak base, the pH should be basic. Now, there are a few exceptions to that, but for the most part, you're not going to see any of those. They would be ridiculous. The ones that are like the shitty acids or the shitty bases, like they're so weak that they don't really count. Okay. All right, so I just did one example with the weak base, not because they're not important, but because we did a lot of examples of weak acid, and what you're going to see is they're almost exactly the same. The only difference is that at the end, you have to turn the OH minus into a pH instead of the H3O plus into a pH, but ice tables and all that. Okay, so I mentioned earlier, when we were looking at KBs, that the Ka table in Appendix D is huge, and the Kb table in Appendix D is tiny. And that's not fair because it's not like there's more acids than there are bases. Every acid has a conjugate base, so nope. Instead, there is a way to convert the Ka value of a weak acid into the Kb value of its conjugate base. Okay, so this equation, the equilibrium constant of an acid, Ka, times the equilibrium constant of the base, Kb, equals 1.00 times 10 to the negative 14th. The way this works, this is the Ka value of a weak acid. And this is the Kb value of, I can spell, the conjugate weak base. So it's the acid version and the base version. We talked about this at the beginning of chapter 16. So if you know the Ka value of hydrofluoric acid, you can solve for the Kb value of fluoride, which is what happened. There's that's the weak acid, and there's its conjugate base. To get this number, all they did was plugged this into the Ka. This equation will always be given to you because it has the constant in it. So it's one more equation to add to our list of equations. Okay. And the way that we can see what we learned at the beginning of chapter 16 demonstrated, because at the beginning of chapter 16, we had that list that had the red and the blue arrows on it and had acids and bases listed, and they were in the order of strength. And if an acid was in the strong acid or stronger acid part, its conjugate base, which was right next to it, was a really weak base. So there's this trade-off, right? If the acid is strong, then its conjugate base is really weak. If the base is strong, then its conjugate acid is really weak. This is just showing us that with numbers. So hydrofluoric acid has an equilibrium constant to the negative 4th, which for a weak acid's pretty strong. F minus has an equilibrium constant of times 10 to the negative 11th, which is really tiny, which means fluoride's a really crappy base. Okay, so this is just showing us that trade-off, but numerically. And if you have something that's about in the middle, so like I've got an acid that's negative 7 and a base that's negative 8, they're both kind of in the middle. Okay, so they're both like, neither of them is super great at what it does, so they're both just meh at what it does. Okay, they're both kind of meh acids and bases. So I didn't have an example using this equation because it's just multiplication and division, but you will get a chance to use it in the discussion worksheet and, of course, in the homework. So one thing that I guess, I'm gonna be super professional here and stop the slides, but not stop the video because I'm a grown-up person. And remind us of our definitions of acids and bases that we talked about at the beginning of the chapter. Actually, I lied. I'm not. we're going to stop this video here, and that's going to be another video.